Okay, so for this lab, we are going to be working on forces um, regarding friction, specifically frictional forces. So let me go ahead and share my screen with you regarding that specific lab. And let's see, we have two labs or two simulations that we're going to be going off of. So this is actually the second lab, so I'll go in sort of a reverse order here. So with this lab, what we're going to be trying to do is we're going to be trying to figure out what the maximum frictional force that you can exert on this this object. And if you look through the directions, I'll probably give you a specific scenario. More than likely, it will be well, it's going to vary from semester to semester. So in this case, let's just say, and we're going to have wood on the table. So to change that surface, what you're going to do is you're going to click the verbiage that says types of surfaces. And so we have glass on glass, graphite on some surface, rubber on concrete, in this case, wood on the lab table. And additionally, you can change the mass by selecting up or down as such. And so you're just going to note what that number is. Now, keep in mind that when you select a mass, for this simulation, it's sometimes a bit harder to get to the that same mass if you have to repeat this experiment. So just be cognizant of that as you go through this. So you want to play around with it a couple times. And the one thing that may happen in certain screens, I noticed, is that this, let me kind of turn this sideways a little bit here. I'm on my iPad. When it comes up, only the top half of the simulation shows up. So you're either going to want to zoom out a little bit or maybe modify your screen somehow. But in this case, you can see I have two windows, if you will, two dotted border windows here that we want to see. And essentially what you want to do is hit the start button. A force will be applied. You can kind of see from the graph there how much force is applied. And then the block begins to move. Now, what we're looking at here is at the chart down below, we're exerting some force. Let me move my inset there. We're applying a force up to the point where the block is exerting, the force of friction is exerting some force on the block and vice versa, such that this block doesn't move. So up to the point where the object reaches its max force, what you can see there is about, let's see, a little bit more than 1.6 newtons. Prior to that, this block doesn't move. So essentially what we have here is we have the maximum amount of static friction in this situation based on the mass and the surface that the block can exert on the surface and vice versa. That's the maximum amount of static friction that the two can apply to one another. So up until then, it doesn't move. Right after that, right about the 4-second mark, which really isn't all that important. But right after that, in this bottom one, kinetic friction now takes place. And kinetic friction is just that movement that takes place. So if I reset this again, and I'm just moving it at a specific rate. And so it's moving at a constant rate, and that kinetic friction is constant, okay? So time really isn't all that important. What is going to be important is what the maximum amount of static friction that the surface is exerting on the object. So pay attention to that. Okay, and then you're going to want to follow the directions here for that was part 2. Let me pause for a second here, and then I'm going to switch over to the second simulation. And the second simulation is that of a block on an inclined plane. Okay, so let's look at a block on an inclined plane. So in this simulation, I'm following along with the directions here that you should have. It'll ask you to, again, select a, this time a coefficient of static friction. And so over here on the right side, you can see the frictional coefficient. So in your book, and in most books, you'll see that as being Greek letter mu with a subscript of S for coefficient of static friction. And for coefficient of kinetic friction, it'll be mu sub K. And also, again, you're going to see that as you scroll through some of these values, it's sometimes a little bit hard to get and repeat that same value. So play around with it initially. You're going to want to set a mass. Remember that your mass is in grams. So if you want to look at something in SI units, you're going to want to convert that into kilograms. Just simply move the decimal over, 3 places to the left, divide by 1,000. And so to change this setup here, what we're going to do is, and in this case, it doesn't tell you what the surface is. It just tells you what the coefficient of static friction is. So you just want to click that button there that says change the angle. The angle is in degrees, so that's one thing that you're going to want to note, and you'll see that later on in the direction. Just let this thing go up until this thing begins to slide. So if you want to, you should probably want to freeze it so you can figure out exactly or roughly about the angle, and then repeat it again. So if I repeat this again, this time I'm going to try and capture it. I think it was somewhere around 20 degrees. So I'm anticipating somewhere around 20 degrees. And then I click the freeze button. And then you're going to want to repeat this about, I think I say 4 times in your experiment. So you want to note what you noticed, and you want to prove this algebraically. So how are you going to prove this? So this is where the summation of forces comes in. So let's look at the summation of forces, and we're going to also look at a free body diagram simultaneously. Okay, so let's look at an example. Now, this is not the exact example. This is something similar, and let's look at this. So this is a problem. This is one of my old problems. So let me see if I can mark on this a little bit here. So a couple of things to note here. In your situation, there's no motion, so you want to take that out in this example. And in this case, it's not f of k, it's going to be f of s. That's going to be going up the ramp. And I'm not going to give away the entire problem, but in this example here, the forces are pretty much in the same directions as you have, and it's done a little bit differently. So you're gonna have to work your way through this. The weight is downward, and that's the force that you're gonna need to resolve. You're gonna want your XY axis in a fashion similar to this, where your y-axis is perpendicular to the surface of contact, and then your x direction really doesn't matter which, if positive is left or right, as long as it runs parallel to the board. So this XY axis can be set up in this fashion as well, and that should be it. And then now you're going to sum the forces in the various directions. So you're going to keep in mind what forces go in the x direction. In this case, you're going to want to change that to f of s. And then your other force, which is this force here, is also in the x direction. And I said that down the ramp was positive, and you have that. And by Newton's second law, you have this equation. All right. And then here's your second equation, which sums the forces in the y direction. So the key here is to recognize that which force initially you want to resolve. And the force that you want to resolve in this situation is the force that is not parallel or perpendicular to one of your axes here, your XY axes. And that's how we recognize that the weight needs to be resolved. Keep in mind that this angle here, theta, is the exact same angle here that's going to open up as this thing begins to elevate. You can see that a little bit better from the free body diagram. Okay, and so you should be able to gather up a lot of information from the simulation as well. And hopefully that will help you get through this experiment. If you have any questions or concerns, feel free to give me a call, 727-791-2503, or you can give me, or you can shoot me an email. All right, you guys take care.